Hello everyone, my name is Joel Bell and I am the International Development Manager for RTP Company. Today I'm going to be giving you an engineer's guide to specifying the right thermoplastic. Very quickly before diving into that topic, I have several slides explaining who RTP is. So RTP is an independent specialty compounder. We are a compounder, meaning we blend thermoplastic resins with a variety of fillers with the intention of creating specialty compounds. We are independent in that we are not owned by a supplier of any of the materials we compound. So we will suggest the best solution or solution options for you, the customer, to select. Whether you need a very specific compound or an unfilled resin for your application, we work in every thermoplastic resin system with hundreds of modifiers to develop the right solution for you. We sell more than 9,000 different types of compounds each year in pellet, sheet, and film formats, and of these, roughly 1,750 are new formulations. We categorize compounds into product families according to their general attributes. These are color, conductive, flame retardant, structural, wear resistant, and thermoplastic elastomers. These product family attributes can also be combined to provide you with a single material that covers multiple challenges. We understand the unique requirements of a diverse set of markets, and each of these rely on us to provide outstanding solutions to their application challenges. Our materials can be found in everything from simple toothbrush handles to complex aerospace applications. We are a very well-kept secret for many large companies. In fact, we provide the thermoplastic technology behind some of the most famous brands in the world. We have over 20 production plants and even more sales offices located around the world. We are well equipped to serve you with consistent thermoplastic materials, wherever your facility or facilities may be located. Okay, so today's agenda will include defining compounding, what the plastic resin selection process is, how we use compounding to enhance performance with some specific case studies, and we'll discuss several new RTP technologies we can offer. Okay, so let's dive into compounding. The objective of any compounding process is to disperse any agglomerates into their smallest particle size and to achieve good distribution. These are both very important. Here is a simplified depiction of the compounding process and equipment used to convert raw materials to finished product. In the upper left is a simple example of glass fiber, blue pigment, and resin. These are introduced at the beginning of the process through a variety of methods, and then the main work of dispersion and distribution is completed inside the extruder. At that point, the molten resin comes out like spaghetti strands and needs to be carefully handled through cooling, pelletizing, and then classification into our finished pellets, which you can see in the upper right-hand corner. The customer will then use these pellets in their conversion process. So let's dig a little deeper inside the extruders. RTP uses three types of extruders to meet our compounding objectives. All can achieve high distributive mixing. The twin screw and co-kneader have the best dispersive mixing capabilities for fine powders, but the single screw is also a very powerful tool. So let's put it in perspective. Compounding extruders do a considerable amount of work. Many of the additives have extremely high amounts of surface area, which must be completely wet out, coated by the plastic resin. So carbon black particle, as depicted in the picture, has a surface area of 130 square meters per gram. So there's a lot of surface area. On the flip side, a football field or soccer field has a surface area of 4,460 square meters. So that is equal to about 34 grams of carbon black. In a conductive compound, for instance, there would be 20% carbon black, and the objective of the compounding process would be to wet out the surface area. Wetting out that amount of surface area is similar to coating the entire surface area of the soccer field with only 136 grams of plastic. It's a lot of work. Okay, so now that we have a brief overview on the compounding, let's take a look at the plastic resin selection process. Since there are over 60 thermoplastic resins and hundreds of additives available, these can be combined in different ways to produce thousands of thermoplastic compounds. This creates the dilemma for plastic part designers. Which one do I choose for my application? RTP Company helps our customers through this selection process by using a simple yet effective and straightforward selection process that uses 3 steps. Step 1, use resin morphology. Step 2, use thermal and cost requirements. And step 3, fine-tune and add special features. In step 1, we look at the morphology of thermoplastic resins, which is simply the form and structure that the molecules of the polymer take as the polymer goes from the liquid to solid phase. In thermoplastics, you will find 2 types of morphology, either amorphous, where you have random molecular orientation, or semi-crystalline. Some of the molecules orientate into crystals. The amorphous resins exhibit the positive morphology features of low shrink, low warp, tight dimensional tolerances, and transparency, of course, except for ABS and HIPs, which contain opaque rubber compounds. They exhibit the negative features of poor chemical and abrasion resistance and poor flow into thin wall sections. The semi-crystalline resins exhibit the positive morphology features of excellent chemical and abrasion resistance. They have good flow into thin wall sections. They exhibit the negative features of poor dimensional stability, and they are opaque. So if we divide the different resins available into the 2 categories, you have a list like this. Since about half of the thermoplastics are amorphous and half are semi-crystalline, your choices now have been cut in half. I have arranged my list such that as you go from the bottom to the top, 2 properties are increasing. What are these properties? Thermal performance and cost. So based on this, I can further group each category of plastics into 3 groups. Commodity resins that typically cost less than $1.50 per pound, engineering resins that typically cost $1.50 to $4 per pound, and high performance resins that can cost anything over $4 per pound. By using morphology, cost, and thermal performance, your resin choices are now quickly reduced to maybe 2 to 4 options. We can typically further look at special features and fine-tune that list to 1. Okay, I've shown how we can narrow down resin selection based on morphology features, but various applications have conflicting morphology requirements. Let's show how we can overcome these conflicts by compounding. So looking back at the various morphology features, we can chart with an X which belong to each, and also put a D where they are deficient. We can see that the amorphous morphology will have deficiencies relating to mold flow, chemical resistance, and wear resistance. The semi-crystalline morphology will have deficiencies related to dimensional stability and transparency. So now let's see how these deficiencies relate to some specific applications. The first application is an automotive oil pan. This application needs chemical resistance, strength and stiffness, good heat resistance, extremely tight dimensional stability and flatness, and also reasonable cost. Because we have conflicting morphology requirements, there is not an obvious choice. A semi-crystalline material would give the chemical resistance, but an amorphous material would be needed for the tight dimensions. So let's dig into the dimensional stability. The question is, can we reduce the shrink rate of a semi-crystalline resin and make it dimensionally stable? The picture shows how different shrinkage can cause deflection and warpage in a complex part. One way to reduce the shrink rate of a polymer is to add glass fiber. Because glass fibers align themselves in the direction of mold flow, glass fiber will have a tremendous effect to reduce the shrink rate in the direction of mold flow, the X direction. However, they do little to reduce it in the transverse to mold flow direction, or Y. This differential shrink rate leads to parts warping and twisting. Instead of adding glass fiber, one could add a low aspect filler, such as mineral or glass bead. This will reduce shrink rates in both directions and result in a flat and dimensionally stable part. However, low aspect ratio fillers do little to improve strength and stiffness. So what is commonly done in the compounding world is to add a combination of glass fiber and mineral or glass beads. For instance, they might use 15% fiber and 25% mineral. This helps to achieve a dimensionally stable part with strength and stiffness from the glass fiber. So if we go back to the automotive oil pan, we see that a nylon 6,6 semi-crystalline resin with a glass fiber and mineral mix is used to counteract the conflicting morphology requirements. And that is the type of material typically used. Okay, so the next is a lawn tractor hood. This application needs tight dimensions and flatness, reasonable cost, chemical resistance, good flow in the mold, and also high impact. Again, we have conflicting morphology requirements, and there is not an obvious choice. A semi-crystalline material would give the chemical resistance and mold flow, but an amorphous material would be needed for the tight dimensions and good impact. So let's dig into the chemical resistance and mold flow. The question is, can we improve the chemical resistance and ability to flow in the mold of an amorphous resin? One compounding technique to do this would be to alloy the amorphous polymer with another polymer. To improve the mold flow of an amorphous polycarbonate resin, one can alloy it with a low melt temperature polymer such as ABS. This alloy has improved flow. However, since both polymers are amorphous, the chemical resistance of the alloy is not much improved over the initial polycarbonate. So what else can we do with alloying? By alloying the polycarbonate with a lower melt temperature semi-crystalline resin, such as PBT or PET, one can produce an alloy that has both better melt flow and chemical resistance versus the polycarbonate. If done properly, we can maintain the impact and strength properties as well. So if we go back to the lawn tractor hood, we can address the conflicting morphology requirements with a PC-PBT alloy. Okay, the third application is printer gears. This application needs extremely tight dimensions, reasonable cost, good abrasion resistance, low wear rates, and low friction. Again, we have conflicting morphology requirements, and there is not an obvious choice. A semi-crystalline material like acetal would give the wear properties, but an amorphous material would be needed for the extreme tight dimensions needed in this application. So let's dig into the wear properties. The question here is, can we make an amorphous polymer, which has the dimensional stability, more wear resistant? One way to accomplish this is to compound a wear-resistant additive, such as PTFE, into the amorphous resin. As shown here, polycarbonate can be made to have similar wear and friction performance as compared to acetal by compounding 15% PTFE into this polymer. So, if we go back to the printer gears, we can address the conflicting morphology requirements with a PTFE modified polycarbonate. Okay, so before I close, I would like to briefly introduce you to some of the new technologies that RTP Company is currently working on. I won't be going into any great detail on any of these, but if you have interest, please make a point to visit our virtual booth. Okay, so the first area is healthcare, and this is a hot topic in our current lives. RTP 2000 HC series was recently developed in response to healthcare industry's need for plastic housings that could better withstand the harsh chemicals that are now being used to disinfect hospital equipment to prevent the spread of infections. This technology may also be translatable to other non-healthcare applications where housings are seeing frequent cleanings and additional sanitizers. These compounds have good dimensional stability with shrinkage similar to polycarbonate ABS blends, and there's also a flame retardant grade for electronic housings, and that is RTP 2000 HC FRA. The second area is color. Anyone that has gotten into a dark colored car interior in the middle of a hot sunny day knows that dark colored plastics typically absorb a tremendous amount of heat from the sun. Much development has been going into pigments that absorb light in the visible spectrum, producing deep, rich colors, but reflect light in the heat-generating infrared spectrum above 700 nanometers that is given off by the sun. These special pigments result in dark colors that remain much cooler when exposed to sunlight. Areas where that might be useful are patio furniture, decking or pavers, roofs and siding, and also automotive interiors. The third area is flame retardants. RTP-FR engineers have been developing plastics that meet the requirements of UL 2043, which is for plenum applications, or you can think above the ceiling. UL has unique requirements for low heat and smoke release in these applications that has previously limited them to metal components. RTP has now expanded the materials to include FR polypropylene and FR nylon compounds. There are a number of opportunities, including wireless access points, speaker housings, vent diffusers, cable racks, and light housings. The last area is wear. If debris gets into a system, it can cause catastrophic damage. Often, ultra-high molecular weight polyethylene is used because it is one of the most abrasion-resistant plastics. However, it's not injection moldable, so it is somewhat limited in its use. Parts must be machined out of a bar or rod stock, resulting in loss of productivity. RTP company tribologists have developed a polyolefin alloy that has similar abrasion resistance to the ultra-high molecular weight polyethylene, but it is injection moldable. This opens up a lot of options for abrasion-resistant part design. And that just gives us a small slice of the many technologies we continue to work on at RTP. So in review, this presentation introduced you to compounding, including the objectives and equipment we use to achieve good mixing. It introduced you to the dilemma many face when trying to choose the proper material for an application. And it revealed to you the process that RTP company uses to simplify the resin selection process. It showed you how we can use compounding to overcome some of the resin deficiencies for those applications that require both an amorphous and a semicrystalline morphology. Finally, I introduced you to a few of the new developments at RTP company, and I encourage you to interact with our virtual booth. With that, I would like to thank you for your attention, and my contact information is listed for any questions you would like addressed. Thank you.